Hi, welcome to Teardown Tuesday. We've got the Compucorp 322G Scientist, programmable scientific calculator dating from 1973. So yes, that makes it more than 40 years old. Fantastic. Thank you very much, James from Sydney, who saved it from the Sydney University dumpster. And you've seen this in a previous mailbag. He sent it in, and it's just a beautiful looking device. There's something sexy about it. Its keys on it are absolutely horrible. Some of the worst spongy keys I've ever felt in my life, but I don't know, it just looks really quite neat. I like it, and it works on 4 D-cell batteries, as we saw, and I tried to power it up in the mailbag video, but yeah, it drew like much more than its rated current of 1.3 amps when I tried to power it 7 volts through the jack there. But anyway, it is a beautiful machine. 1973 vintage. It's got a gas plasma display, manufactured by Burroughs, I believe. So anyway, it should be real interesting inside. Let's take a look. There's going to be lots of discrete stuff in here, I suspect, and I can see inside the battery compartment multi-board construction. So let's get into it. And here we go. It already came with these screws undone. There were just 2 more in the battery compartment there. So let's crack it open, and hey, we're in like Flynn. There we go. Oh, look, you can see the you can see the nipple there on the gas plasma display. Doesn't that look nice? There we go. That instantly dates it. There we go. The 48th week, 72. That display was manufactured. Got a couple of, oh no, they're nuts. I thought they were trimmers there for a second. No, a couple of nuts. So let's. Hey, yep, the whole thing just lifts out. Look at that. There we go. Hey, not as discreet-y as I imagined. I expected like a whole bunch of dense TTL stuff, but it looks like it just looks like we're going to have some LSIs in there that do all the magic. So presumably I got to take out little spring washers there off the off those, and the boards will just lift out. Now what's interesting at first glance is, look, they've got like the plug-in card edge connectors over here, and they're not actually connected up. There's nothing in the case or anything like that that joins them together. Like there's no bus on the end of it, or no backplane on the end of it that joins these boards together over here. So that must be for production testing. I would presume that they can then like plug those boards into a test jig in the production factory and test them. That'd be my guess anyway. But this is how they're joining the boards together using this stack arrangement here, and they plug in. So this is like a backplane connector. You can see the cards just slide into there like that. Oops, sorry, I've had my camera white balance switched to auto, so the colors may not have been perfect in the previous things. That was from the trade show that I went to. When I go to trade shows on site, I just whack automatic white balance on. Anyway, it's fixed now. So here we go. There's the 16-digit gas plasma display. That looks really quite nice, and of course this whole thing just lifts out like that. We've got a flat flex going over there. It's multiplexed, of course, and well, let's try and get all these boards out of here and see what we can get. And here you go, we're in. There's the 2 main custom LSIs, and I'm not sure why I sort of expected this to be chock full of like a TTL or other, not necessarily TTL, but like chock full of logic. I don't know. Anyway, that's the back of the keyboard there, the keypad. So that's got Teledyne Kinetics Series K patent pending. Thank you very much. I think your patent's expired by now. But yeah, these are manufactured by Texas Instruments, and they're clearly, and there we clearly custom LSI chips. There we go, dated 29th and 34th week 1972. So all the magic happens in there, and not much else. We've got some UMP 480s. They're obviously driving, I don't know what they are offhand, but and a whole bunch of transistors. They're obviously driving the gas plasma display up here, and we've got some funky looking old school foil caps in there, and well, that's about it. Double-sided board, just all tin plate. Nothing fancy going on there at all. A few diodes, a few resistors, and nothing obvious blowing yet that I can see that's causing the issue. By the way, boards are tied together with just these, so there's only a couple of, like, apart from the big parallel connections on the back, they've obviously got, I don't know, some sort of power or something going over there. Why they didn't put it all on the card edge connectors at the back, I don't know why they still need to do that. Not a bit disappointed, not as dense and impressive as I thought. Yeah, it takes all the shine off it when all the logic's inside a couple of custom LSIs you'll never get the data on. And they've obviously got a compression fit on these card edge connectors over here, because they wouldn't budge until I loosened all that. And there we go, they all come apart. I'll show you that in a second, but obviously that has got, you know, they're using all the contacts in there to get power through. They got some logic on there, but apart from that, the bottom side here, woohoo! And if you're wondering why they've shorted out all these contacts here, because this slides into the, and there'd be pins on the bottom there shorting out, well, this is just one big heatsink. You can see the screws there. They've got some Loctite on those, and they're just these little power transistors there, and they're just heatsinking those. So this is the power supply board, and, you know, not a huge amount doing here. It looks like we've got an inverter for the gas plasma display, hence, you know, that separate cable we saw jumping off to the main one. And here's our power input here. So maybe there's something wrong around here. That could be possibly why it's not working, or when you power it from the batteries, or it's drawing too much current when I power it from the plug pack. So, well, apparently. So there's got to be something wrong on there. And of course, this is a battery powered calculator, even if it is D cells. So they've sprung for the 74L series here, the low power TTL stuff. Beautiful. And here's our memory board. Take a look at this. We've got ourselves ROM and some RAM here, and obviously some sort of memory controller ASIC. Once again, all designed by, well, manufactured by TI. Yep, 39th week 1972. And these are obviously our program ROMs here. No, they're not EEPROMs. They're because there's no window on there. They've definitely got those soldered shut. So they're definitely write once ROMs. And check it out. We have an Intel P2102. We've got 4 of those, and that's going to be the RAM for this thing. I couldn't immediately, I know it's an Intel SRAM, but I don't know what size. So this thing has 80 program words of memory, so obviously it's got to have some, unless some of them built into the processing ASIC, which we'll see. Obviously the processor is going to have some registers and stuff like that, so I'm not sure if this is just storage memory, or whether or not it's actually used for you know, intermediate calculations and stuff like that as well. But yeah, 80 program steps, so it's got to at least store that. Most likely battery back there, or I don't see any sort of diode kind of thing happening for the power on that, but that would be, I mean, they've got to keep the contents of that when you turn the thing off. Otherwise, well, I believe it's got non-volatile. I'm only assuming. I don't actually know whether or not it keeps the contents when you turn it off. Kind of be stupid to have to reprogram in your 80-step program every time you powered it on, but I don't know. Could be. And this is actually our main processor board. So those 2 Texas Instruments ASICs we saw on the display board, they're probably, like, you know, a display controller. There could be additional processing as well, but yeah, here we go. I mean, you know, 07, 06, 05, 04. Let me check. Has the other one got 03? I don't remember. Yeah, 02. There we go. Oh, 02 and 08. So this one, there we go. 03. Where's 01? So they've got at least 4 chips to do this, and the processing architecture, I don't know. You know, whether it's a 4-bit, 8-bit, or whatever, or 64-bit processor, I have no idea whatsoever. If you do, please let us know if you've got any, especially you know, internal block diagrams, you know, architecture information on this sort of stuff, please let us know. So this top display board here, they actually call that the D-scan board. All these boards are labeled, but yeah, I guess that's a display scan, right? So obviously they are the two display multiplexer, you know, processors. They probably, of course, would contain registers to handle the display data. So the processor would just offload the data, and then this would handle updating the display and keeping it multiplex. So that's, you know, that's that entire board. I think it's just dedicated to that display stuff. So it really is quite a nice and modular design here. I mean, you know, they made it easy to service, to test. As I said, you know, they've got these test card connectors on the side, so they can probably test all this jazz. So we've got our display, and then we've got our main processor board. I mean, look, there's bugger all on there. Look at that. I mean, there's no even well, they've got some, I presume that's bypassing on the one input there, but there's like, they don't even bother. The thing's probably so slow, it's probably running at, you know, hundreds of kilohertz or something like that. They're probably, you know, not worrying about bypassing. That's why you won't find them on any of the other chips. So that's the processor. And then the memory board over here, look, you know, there's no decoupling here. It's just not fast enough. It just doesn't need it. And then a power supply board, so very nicely modular, and they can plug it in and test the damn thing. So that is really quite a nice modular bit of kit. And then there is our pressed together, check that out, there we go, our pressed together card edge connector. So presumably, like, the contacts are just shorted from one side to the other. I'm don't know, I have to measure that. So let's test that theory, that the top of here goes to the bottom of this one, and yep, it does. Check it out. Yeah, that's just not coincidence there. Yep, there you go. So that's how it's designed. So the, like, the top of, sorry, the bottom of this top board here goes to the top of the board below it, and then so on. So you'd have to design your board architecture and your pinouts to match that sort of stuff, but that's how they get the data between boards, and it's all sandwiched together, and once you screw that on, it actually becomes quite a rigid structure that holds the board in place. I don't mind that at all. That's quite novel. So I'm a little bit surprised at the sort of lack of density in this thing. Like, you know, I expected, like, all dip technology, of course, back then, but I expected it to be, you know, like chock full of dip chips on each one. Like, I expected sort of, you know, this total number to be sort of crammed onto one board, and I don't know, maybe they used a, you know, a 4-layer board or something really fancy like that. But no, you don't have to when you go for all these ASICs. But they're certainly designed, and they had to split the processor up into 4 separate ASICs. So I'd love to know what the architecture is there that made them do that. And the display processor, they couldn't fit it in one, so they had to use 2. Probably this is some sort of like gate array or something like that. So, you know, they only had a certain amount of logic, and they had to design their processor using a custom gate array. So it's probably like a gate array chip. So it's not actually, probably not a custom ASIC as such. Now what I've done here is I've powered it up. I know it draws like 2.4 amps or something, 2.3 I think, just irregular. So I've taken out the board, taken out the power supply board here, so it's not powering anything. I've still left the gas plasma high voltage display plugged in, and well, it's drawing 1.1 amps at the 6 volt, nominal 6 volt battery supply. Well, 6.8 watts just for a power supply sitting there doing naff all. Wah, something's wrong. Now if I have a look at the output voltage from this inverter here, hey, there we go, 62 volts. There's another wire there, minus 56 volts. Okay, now we're starting, now we're talking. So, yep. Oh, there. So you combine those, and yeah, that can be reasonably dangerous. So you don't want to go touchy-feely around there, that's for sure. So, you know, I don't know what it runs at, but hey, sounds, you know, it sounds reasonable anyway. It's a high voltage inverter, so that works. But yeah, where that damn 1.1 amps is coming from, I got no idea. Okay, I've disconnected that. Let's see what we get now. And, oh, bingo, look at that. So that display, we're only getting, oh, you can't see that, but only getting half a watt, or 0.8, sorry, 80 milliamps. So at 6 volts. So there you go. That display could be cactus. That, yeah, I don't know. Is it supposed to take that sort of current? I don't think so. Because the rating on the back of the case here, it says 7 volt supply at 1.3 amps. So, you know, with everything, I'm almost getting that with just the plasma power supply hooked up. So, what? Alright, now I've disconnected this display processor board over here from the display, and we'll just power that on again and see what we get. Yeah, we're still getting an amp. So, nothing to do with the gas plasma display itself. Something on that display processor board is chewing an amp. And I'll get my Bryman BM257 here. Very nice little meter, by the way. Nice little compact meter if you're after a nice cheap one. And it's got a low impedance check function, so we can use that to drain the cap. I measured this cap here. It's got, during operation, the full 128 volts across it, so we can actually use that to discharge. Now, cap on there, it's not going to hold a lot. It's only 0.5 mic, so, you know, it's not much at all. So, there we go. There's no voltage left on it. It's just going into auto mode like that. So, yep, that's fine. Discharged. Can safely work on it. So something has failed on here. What? Well, it's drawing excess current. So something is going to be shorted or loaded down severely. Diode test. There's a diode here. I mean, you know, here's our input over here. So there's no connections on the bottom. If you have a look at the bottom there, so it's easy to see all the traces going on top. I love tracing these. They're just, you know, so easy to do. And going over to the diode there, so first thing we're going to check is that diode. That looks okay, no worries there at all. We're getting our diode drop, so that's fine. So yeah, we're getting a short somewhere else. The thing I'm going to test next, that main capacitor there. Although, as I said, I measured the voltage on that. I was getting 128 volts. So we'll switch that back to ohms and give that a whirl. As I said, we've discharged that. Otherwise, it's going to affect our resistance reading. No, there we go, 7 meg, and someone's calling me. Better go answer it. So that's exactly what you'd expect from a good cap. It's just going up and up and up. I mean, we can whack it into capacitance mode, but whether or not that's going to do any good in circuit, this is half a mic, so let's have a look. But it's not shorted. I mean, we're basically looking for shorts, so yeah, no, it doesn't like that. Maybe it's got some residual voltage on there or something like that from the charging from Evo, from the original charge. We didn't discharge enough, or maybe from the resistance test function. So it's obviously having a big issue with auto ranging there, so we could. No, this one doesn't. We can't manual range our... Oh, look at that. Auto range only. Forgot about that. Oh, that's a bit annoying. Here I was saying this is a decent meter. Well, it still is, but yeah, it doesn't let you manual range the capacitance. That's crazy. Anyway, next thing I'm going to check is the other caps. I mean, before we start mucking around with semiconductors, you know, these are, I don't even know the pinouts. What is it, UHP 480? I don't know, and you don't know the pinouts for the custom ASIC, so I don't really know where the rails are here as such. So let's start measuring some caps and see if any are, that's a pretty consistent 7 nanofarads there. There's probably nothing else in circuit there. Hey, there we go. There's 7 nanofarads a pop. And no, it doesn't like that one. That one's got something in circuit. We can go to our resistance range there, see if that's shorted out. Oh, 2K, you know. It could be something in circuit, so I'm not too concerned about that. I'm looking for gross shorts at the moment, so let's measure the other caps here. 7 nanofarads again, bingo. Alright, we should try and change the polarity on that one. That one is, again, looks like it's low impedance. 7 nanofarads, pretty close. So let's go back. Measure this one again. Hello? Hello? Well, there's your problem. Dead short across that cap. So, ouch. Ouch. That could be an issue. We could have ourselves a dead cap there. 7 nanofarads. Yeah, 7. Doesn't like that one either. So let's go back. No, that's 1.2K. But that one... Look at this. I originally thought, here's the cap. Here are the 3 caps. There, there, and there. And it's the center one that's shorted out. And I thought that track was, at first glance, going straight across to there. But it's not. It's cutting short. But look, that's pretty darn close down in there, isn't it? But it's not. But geez, yeah, there's no little bridge in there or anything, but maybe the top side, I don't know, we'll have to suck the cap out and see. Oh no, wait, look at the top side here. What's that little dag in there? Like that, that could potentially be shorting out, maybe. I'm going to get the knife in there and give that a little scrape. It doesn't look like it's touching, but geez. Alright, so I've lifted that out, and there appears to be, I'll show you this close up in a minute, like a white residue or something on there. So, yeah, that cap is definitely shorted. That ain't right. So, yep. That, well, I don't know if it's going to solve the problem, but it definitely is a failure point. So check out that residue on that capacitor, and it's like all the ones next to it have that residue on there. So yep, that cap has gone blah. And you can see there's evidence of some of that on the bottom of this cap over here as well. So yeah, you just change that one as a matter of course too, even though it hasn't shorted like the other one. Alright, I didn't have any axial capacitors, but yeah, I had some radial ones. I'll just bend the leads. I've probably got some old axial ones somewhere, but probably not the right value. Anyway, 5600 puff, it's going to be near enough. I doubt that it makes a major difference. I changed the 2 that were leaking, I guess, with that white crap oozing out. So let's power it up. Hey, that's better. There you go, 0.5 amp. Awesome. So that was definitely some of the current draw right there. So with all boards plugged in now, I'm getting, you know, almost 2 amps. So that is higher than the rated current on the back there of 1.3. And if I power up just the power supply board on its own with the display supply disconnected, we're getting 90 milliamps. So that's pretty much, you know, what you'd expect ballpark for the quiescent supply of something like this old school power supply. So, you know, no problems at all. We're basically looking for gross excess current faults here. And let's check the power rail here and across this main filter cap up here, and bingo, 4.9 volts. Presumably it's 5 volt logic, and well, I'm happy with 4.9. That's certainly well within spec. So yeah, like, you know, 5 volt logic, they've got 7.4 TTL stuff in there, so, you know, they're going to have a 5 volt supply everywhere, you got to presume, so that's okay. So all the logic is powered up. And if we have a quick little probe around here, there's our 5 volt rail, so that's doing hunky-dory, no problems whatsoever. There's no ripple on that, and we've got all this bus stuff happening over here. So let's start probing some bus. Hello, hello, Mr. Signal at 10.1 kilohertz. Okay, there we go. Yeah, 10.1. Yep. Oh, hello. So it's working. Hello. Bit of round in there. Look at that, 200. It's almost bang on 200 kilohertz, 203 kilohertz there. So we're getting some activity. So, oh, yeah, that's reasonably warm. Yeah, they're actually getting warm to the touch. Oh, that's gone negative. Yeah, there we go. Got a bit of negative stuff happening down in there, yep. But yeah, we certainly have some clock stuff happening. There's that 10 kilohertz and 200, so yeah, it's doing something. It's powered up and she's trying to work. Actually, I just thought of something. The back of this says 7 volts at 0.7 amps, but that may not be able to operate from that. That may just be to charge. If you've got internal rechargeable batteries in there, that may just be the charging current circuitry. So yeah, maybe this, you know, I mean, clearly we found a problem. It was drawing excess current. We fixed that with the shorted cap and stuff like that. But you know, the 800 milliamps that we're drawing with all these boards in, 850 could actually be right, and there might actually be nothing wrong with this. It might be driving. It may be just the display board or the display itself, which is cactus. And by the way, if you want to know what a good quick continuity buzzer here, this one's pretty darn quick. You can, you know, if you're scanning for ground pins to find on this top board, for example, yes, it's powered down. We can swipe along there like that. Bingo, until we got one right on the end. We got ourselves ground pin right there. And if we... So I just soldered myself on a little ground test point there. I've got a resistor just hanging off there. It's a bit bodgy, a bit how you doing, but it just allows us to get in here and probe around. And look, we got some activity there. So that's a win. That's 925 hertz there. That's 5 volts, 2 volts per division. That's going negative, by the way. So that's negative going. So there's lots of negative going stuff happening in here, and that's 10 volts, 5 volts per division, 5, 10, 15, so like negative 15 volts and stuff like that. So yeah, like there's data get into here, and I checked a few supplies on the other supply rail, and yeah, we're getting like a negative 15 supply, and there was a plus 9 somewhere, and you know, other stuff, but you know, we're getting nothing on the display, and I presume that I don't have to, you know, do some sequence to power the damn thing up. So I don't know. Yeah, I would have expected the display just to come on, but certainly getting some activity there. And some of those pins on that chip there, negative 150 volts. That's 50 volts per division. So yeah, serious business. Well, unfortunately, I think I'm going to have to call it quits there for today, and we got some progress on the repair of this thing, but who knows, you know, maybe it's just not repairable. I don't know. If anyone certainly has schematics for it, that would be very nice. So anyway, I hope you enjoyed that teardown and a little bit of troubleshooting there of a 1973 vintage scientific desktop scientific calculator with a whopping 80 words of program memory, and it's a bit of a beast and quite simple. And as I said, if you do have any info on the gate arrays or ASICs used in this thing, please leave it in the comments as well. So hope you enjoyed that, and as always, you can discuss it over on the EEVblog forum. Links are down below, and also there's a link down below to the high-res teardown photos of this. I mostly take photos as I go along, and they'll be on eevblog.com. Catch you next time.